Okay. Today I will speak about a subject called the Liouville quantum gravity. And this is a theory of random surfaces induced by a function mentioned in Vadim's talk called the Gaussian free field. And I'm very happy that Vadim didn't give a definition. So I have the opportunity to define Gaussian free field. So it is a random function defined on the Holden domain. And the way it is defined is by a random Fourier series. So you consider the non-constant eigenfunctions of Laplacian on this domain, normalized in a certain way, and then you just consider the IID sequence of Gaussian variables, the random Fourier sum. You can show that it converges in a negatively indexed Sommelier space. And this random function using this negatively indexed Sommelier space is called the Gaussian free field on this domain. And it is a Gaussian generalized function in the sense that if you want to characterize this covariance, the only way to do it is by doing this for the test function. And in this sense, this covariance of Gaussian free field is it has some logarithmic similarity. And because of that, it is not pointwise defined. So if you really want to simulate Gaussian free field, so these are the two ways to do it. So here, what people do is you use Gaussian free field to convolve with some bump function or the circle average, and this is what happened after you convolve that. And as this thing tends to as the smoothifier tends to 0, this will go out into a very rough function. And the other way is sampled from you would consider a discrete graph, and then you use the discrete Laplacian to sample a discrete Gaussian free field. And these colors represent, so the darker color means you have a higher value. Okay, so the way Gaussian free field define this random geometry called Liouville quantum gravity is the following. So given any planar domain, and consider a variant of Gaussian free field. So here, by a variant of Gaussian free field, I just mean you have a Gaussian free field plus a certain continuous function. So any function who can be written as a Gaussian free field plus a continuous function, I call this a variant of GFF. And the Liouville quantum gravity is a random geometry defined by following. So basically, there is a parameter gamma between 0 and 2. And with this parameter, I can define the random area of the following form. So as we saw, the Gaussian free field is not a continuous function. So this thing doesn't make regular sense. The way to make sense of it is by doing this regularization and normalization procedure. And this procedure has a name. It's called the Gaussian multiplicative test. You can show that this procedure will give you a non-trivial random limiting area as if and only if gamma is between 0 and 2. And similarly, if you have a domain with a non-trivial boundary, you can also use the same procedure to define the boundary line. And so using this regularization and normalization procedure, you can also define a random metric induced by this expansion of Gaussian free field. But this is like a much more complicated procedure. For example, like even the right exponent you need to put to induce the metric is only known in such a value, which is the Schramm-Loewner third case. And I will comment on this nonetheless, this very difficult part has also been done recently. So now, given an instance of Gaussian free field, we can introduce a random area, a random line, and a random metric on the planar domain. Altogether, this defines random geometry on the plane, and we call this Liouville quantum gravity induced by this Gaussian free field. Okay, so the fundamental property of this random geometry is that it has a conformal covariance property under conformal map. So suppose I have two planar domains, and suppose they are related, and by Riemann mapping theorem, they are always related by some conformal map. Right? Suppose the domains are simply connected, and then one can show that if you define this H2 top to be the following one, then these two random geometry, they are the same. So this conformal map is a isometry between these two random geometry. And because of this, we can view these two random geometry as the two different coordinates of the same surface. It is similar to the case of remaining manifold, and in the remaining manifold case, so we can embed this remaining manifold into different coordinates, and they are deferred by some conformal map. And here, this is the quantum version of that. Okay, so this naturally defines the equivalent class between this domain and the Gaussian field pair. So when these two things, they are related in the following way, I can view them as the same surface. And this domain field pair under this equivalence class is what people call quantum surface in this Liouville quantum gravity random geometry. And this is the main object of interest in this theory. So that's why I'm saying Liouville quantum gravity is a theory of random surface, and it is about these kinds of surfaces. Also, for the purpose of this talk, I want to classify so the questions about Liouville quantum gravity into two kinds. The first kind is what I call local questions. By local question, I just mean that it doesn't really depend on what kind of variant of Gaussian field you consider. It only concerns on like local behavior. So one of the typical questions is, what is the Hausdorff dimension of this metric space? This doesn't depend on the precise law of this Gaussian free field. If you perturb by some continuous function, it's not going to change the fractal dimension of this metric. And this is a classical and still open local question. We only know that when gamma equals square root of a third, this dimension equals 4. Other cases is outside of the question. And there are some other, this is something I don't want to explain, but basically whenever you see a dimension of exponent, this question is going to be a local question. And but on the other hand, so in my talk, I will care about things about the integrability, which is when can you compute certain formula for certain observables. And if you want to compute a certain formula, the law of the field is really important. And in order to hide some nice formulas, you cannot consider arbitrary quantum surfaces. You really need to consider quantum surfaces which are nice. And in this theory of Liouville quantum gravity, there are two ways of sampling what I call nice quantum surfaces. One way is coming from scaling limit of random parameter maps, and the other is something called the conformal field theory. And in the next part of the talk, I will just give you a few examples of the two kinds of random surfaces defined in these two ways. Okay, so the first way is the quantum surfaces coming from random parameter maps. So the first example is I have a uniformly sampled triangulation, and the triangulation is very big. So there are many faces, and this defines a, and then you can view every triangle as an equivalent triangle. And then you define a random remaining manifold somehow. And it can be shown that in various sense, this will converge to a random surface, which people call a quantum sphere, with gamma equal to this particular number that I previously mentioned. And so I will not give the precise definition of quantum sphere. For the purpose of this talk, you can just imagine it's defined as a scaling limit of this uniformly sampled triangulation in the scaling limit.
So can I ask you why it's called quantum? Is it mechanically anywhere? Like
yeah, so this is basically a fancy word. So in physics, this gravity is usually corresponding to geometry, and when you have a quantum gravity just means random geometry. Yeah, so but the random geometry is like a low-level word, right? So people change random geometry to quantum gravity just to make it like a more fancy. There are no difference for the purpose of this talk. Okay, so this is the quantum sphere with gamma equal to square root of a third, and it is this relation that allows us to show that the dimension for the Liouville quantum gravity when gamma equal to this is equal to 4. And that's why this is more. But for any other gamma, this is still open. The dimension of this random geometry is still open. And more generally, for any gamma parameter, there is a notion of quantum sphere. And it is originally introduced by Schramm-Loewner to describe the candidate of the scale limit for these kind of services, for certain kind of canonical random kind of maps of spherical topology. And so far, in these kind of senses, it is proved in these works. But I will not go into the detailed definition of this quantum sphere. So the purpose of this slide is just to say that when you can, so one way to define a quantum, a natural quantum surface with spherical topology is to consider some kind of natural scale limit of random surfaces, of random discrete surface. And you can do the same thing if you alter the topology. This is the topology of this. So you can also try to define some the so-called quantum disk. And this picture is this is a so-called circle packing representation of a triangulation where you just view so you view every circle as a vertex and time relation as edge. This is actually triangulation. And there's a conjecture saying that if you circle pack the triangulation in the following way, if you send the number of vertices time to infinity, this counting measure on the circles is converging to this e to the gamma h, defining this Liouville quantum gravity. So this is like a complete way of approximating this Liouville quantum gravity surface. Okay, so these two cases are the uniform case, and so we can also try to make the surface not uniformly sampled. And one way of doing this, this is what I call self-folding work decorative disk. So what you can do is you can first sample a uniform measure on triangulations with a large boundary. And this will be the same in the solid class as this picture. But after I do this, I can be weighted by the number of self-folding paths on this graph. And this will make this picture magnified. And the scale limit of this surface is what people call a two-pointed quantum disk with a certain weight. And this beta can be completely uniform. So basically, this is a way of sampling some random surface with two boundary mark points.
When you say weight, is it just multiplied by the number of paths, or is it?
So the weight is so the weight of each surface is given by how many such kind of separating paths are there. And you also need to times this connectivity constant.
Okay.
But I really need to. Okay, so this is another example. And okay, so the fourth example is what we converge to a quantum sphere with another gamma value. This is a truly non-uniform case. And in this case, I consider a random map, but I weighted by the number of spanning trees. And a spanning tree is just a tree that span over vertices. And if you have a graph, and if you weight it by the number of spanning trees, this reweighting is much more drastic than the previous one. And this will actually change this gamma parameter to another value, square root 2. And you can similarly get quantum surface with generic gamma value using some other models. And one choice is the so-called overloop model. And this is some model depends on continuous parameter. And if you tune this parameter, you are able to get a quantum sphere or quantum disk with a generic gamma parameter. This is how we sample quantum surfaces through the scaling limit of random maps. Okay, so now I want to explain a kind of integrability coming from these kind of random surfaces. So the idea is the following. So, for example, suppose I have a uniform spanning tree decorated surface. There is a bijection between this tree decorated map into this lattice work. So I will not explain how the bijection works. So I'm just trying to draw more pictures to convince you that there is a bijection. So there is a bijection between this kind of map decorated tree with this two-dimensional simple work. Okay, and then once you have this bijection, when you want to describe the scaling limit, you can also view this as the scaling limit of the work. And this gives you a relation between this Liouville quantum gravity surface with Brownian motion. And we know that many things for Brownian motion can be computed. And this gives you one source of integrability of Liouville quantum gravity. And this kind of integrability is also involve another object called the Schramm-Loewner evolution. And the Schramm-Loewner evolution is a class of random curves that describe the scaling limit of certain lattice models. For example, one model is a so-called uniform spanning tree, which is here. And the scaling limit of uniform spanning tree is the SLE with parameter kappa equals 8. So this uniform spanning tree converges to SLE. And then if you have this bijection, what it says is that if you have an SLE together with the Liouville quantum gravity with square root of 2 coming from this picture. Remember this, suppose we have this uniform spanning tree case, this quantum gravity parameter is equal to gamma square root 2. So in the scaling limit picture, I have this on the one side, and on the other side, I have a two-dimensional Brownian motion. And the two-dimensional, so you can compute many things with two-dimensional Brownian motion. And this allows you to compute things on this side. And this type of bijection is called mating trees, because in this kind of bijection, the fundamental thing is always to have a pair of trees mated together. And then you take a scaling limit. And this continuum theorem corresponding to the scaling limit is the so-called mating trees theorem. It is proved in a paper by Dupont, Miller, and Sheffield. And more generally, so if you have SLE kappa, you can change this parameter to a generic parameter. And then this will be changed to another generic parameter. And then you always have a two-dimensional Brownian motion. The only difference is that in the case where kappa equals 8 and gamma equals square root of 2, this Brownian motion, the two coordinates are independent. And if you have this generic parameter, you need to change the correlation of the Brownian motion. The covariance is equal to this. Just like the sanity check, if you plug in square root of 2 here, this is equal to 0, which is the right number for uniform spanning tree. And I want to say that this theorem, although it is inspired by the bijection in the discrete, this theorem is purely about SLE and the LQG, which is in the continuum. And this whole theory is also just developed in the continuum. It doesn't really depend on the scaling limit conjectures, which most of them are open. And this is one example that people can use to, so people can use this kind of mating trees theory to get some exact laws of certain observables concerning random parameter maps and the quantum services. So here, what we consider is this so-called open loop model decorated disk, where I have a disk and I also have a collection loops, and this collection of loops follow some distribution of the open loop model, and then it is conjecturally converged to a random collection curves called conformal loop ensemble with this kappa parameter. So in this conformal loop ensemble, every single curve is a locally look like a SLE curve, and we collectively is a conformal invariant collection of SLE loops. And the underlying surface is also this quantum space. And one of the theorems that people prove is that if you consider the length of all these loops, they collectively given by a jump, given by the jumps of a certain stable Liouville process. And the source of stable Liouville process is basically coming from these Brownian motion things. So there are various ways to construct certain Liouville process from Brownian motion, and this is a source of this theorem. Okay, so this is the one kind of source of nice quantum services and the integrability. So now I want to go to the second case. So the second source is the so-called conformal field theory. Right, so recall that, right, so one drawback of this Gaussian, the definition of Gaussian free field is that if you consider the Gaussian free field on the remaining sphere, this cannot be a conformal invariant function. So in the business of Liouville gravity, you always want to have some conformal invariance. And the Gaussian free field by itself in this complex sphere, it cannot be conformal invariant because the conformal group of a sphere is a infinite group. And if you want something to be Mobius invariant, it has to have an infinite measure. It's kind of like if you want to have a transition invariant measure on the line, it has to be a limit measure, which is infinite. And similarly, if you want to have some conformal invariant random function, it cannot be a probability measure. And this is this basic problem can be overcome by doing a very small twist. So you just consider a certain infinite measure variant of Gaussian free field, which is conformal invariant. And the easiest way of doing this, it appears to be the following way. So you just sample some Gaussian free field on the complex plane, and then you also add in this other simple terms. And this constant C is sampled from some weighted measure on the whole line, and then you just do this summation. And then you get the infinite measure on these random functions. You can show that this guy is invariant under this coordinate change, which means that it defines a canonical random surface which has conformal invariance with respect to this gamma. By the way, so this Q parameter is this one-to-one parameter corresponding to this gamma. So the punchline is that by changing the Gaussian free field slightly from a probability measure to a unit volume measure, we can have some conformal invariant random field respecting this conformal coordinate change in this gamma gravity. And naturally, this gives a natural definition of quantum surface. Okay, so before I talk about the connection between these two kinds of quantum surfaces, I want to first explain something which is nice about this Liouville field. So one thing you can do is you can define the so-called correlation function. And the way to do it is, so once I have the base field, which is the Liouville field, I can also relate it by this exponentials. And this can be realized by taking these limits. And then I can consider this Laplacian transform of the total area. And this is a finite function. And this is a finite function in terms of location of these points and these weights. And this kind of function, it is called correlation function in this Liouville conformal field theory. So the nice thing about this function is that all of these functions are computable. First, so if you just consider the case of 3 points, then just by conformal symmetry, we know that every 3 point on the sphere can be mapped to 0, 1, infinity. And the consequence of this is that the location dependence of a 3-point function is always like this. It's always on the following form. And the only non-trivial dependence of a 3-point function is captured by these by a constant, depends on these weights. And from Liouville conformal field theory, this particular constant, there is a non-trivial prediction of the so-called DUZ formula. It is a very complicated but explicit formula, and it was predicted in physics by this physicist named DOZZ, and it is recently proved in math by Holden and Guillaume Remy. So this is a full detail of the DOZZ formula, which I will not say too much about. The point is that there is a formula called DOZZ formula that computes a 3-point function in Liouville CFT. And another important thing about the CFT is that there is a general procedure called the conformal bootstrap, which is a procedure to compute all the endpoint function from the 3-point function. And this is also rigorously done by for the CFT by these people. And by definition, so the fact that we can compute all the correlation function in the CFT just means that we know the law of this random area for any of these measures. So remember, this measure is the measure of the Liouville field weighted by these insertions. So just to recall, yeah, so these measures, they are defined by these products. So basically, these measures, they define a family of random surface. For all of these random surfaces, we know perfectly well what's the law of the total area. Although it's complicated, it is a formula. Okay, and then there's a similar story for the upper half plane case. So there's also a simple way of defining some infinite volume invariant of the Gaussian free field, which is conformally invariant with respect to this Liouville quantum change. And you can still define this inserted Liouville field, except in this case, you can also have a boundary mark point. So you can have a point in the bulk, you can also have a point in the boundary. And also, when you define this correlation function, you can take the joint Laplacian transform of both the area and length. Okay. And I think maybe I don't say too much about the details about the equivalence. And the punchline is that all the surfaces sampled from the scaling limit of random parameter map can also be represented by the Liouville correlation by this other surfaces sampled from Liouville CFT. And this is a particular example. So suppose I have a quantum surface sampled from this Liouville CFT with this insertion gamma. Then the law of this quantum surface is given by the so-called quantum sphere marked with 3 points. And this kind of thing is true in general. So I think maybe I will not say too much about this part because this is seem to me the least interesting part. So the conclusion is just that I explained 2 ways of sampling quantum surfaces, which are both nice. One way is using random parameter maps, and within that there is a powerful theorem telling you how to compute certain formulas. And then there's another nice way of sampling random surface, which is using this conformal field theory. And there's also a lot of formulas, and they also define some nice surfaces. And then these 2 ways of defining surfaces, in many cases, are equivalent. Just this is a punchline, so then I can escape these details. So this is an instance of the disk case. And we have some general theorem saying that this is basically true. And this is an example by one of my collaborators. Okay. Okay, so now I want to explain. So how can you combine these 2 types of integrability to get some new formulas. So we have this one coming from this type of mating trees formulas. We have something coming from conformal field theory. And how do you combine these formulas to get some new things? And the idea is to use the cut and glue these quantum services. So this is a simple instance of how these cut and glue things work. Remember, we have this previously. We saw one of the natural quantum surface is this self-Holden walk decorated quantum disk, right? And this converges to a certain kind of like a two-pointed quantum disk with a certain weight. Okay. And combinatorially, this can just be decomposed into two uniformly sampled disks, conditioning on their boundary lengths being the same. And then we can just take a skin image. We see that if we glue together two quantum disks with no other things, then the result is this two-point disk with this particular weight decorated with a random curve. And there's a conjecture saying that the self-Holden walk converge to SL a third. And so in the general case, if you have some general gamma value, this will converge to some gamma square parameter. And this gives you a example of saying something like, if I cut a canonical quantum surface using SLD curve, I get two smaller canonical quantum surface. And this type of things, this is called the conformal volume of quantum surfaces. Okay, so this is one example of these things. And so this kind of quantum surface gluing and cutting thing, it provides a recipe to compute certain quantities. So the general recipe is that we just write down a certain conformal volume equation, and then we find a observable that we can compute from both sides. And in some cases, you are very lucky. So within this equation, you can find some quantity which is not previously known. And then you can use the equation to solve that quantity, and you can write a paper about it. So, and the ingredients of this recipe are these kind of two types of integrability and the equivalence of these two different kinds of natural random surfaces. And also this cut and glue quantum surfaces using these SLD curves. So with my collaborators, we proved a bunch of instances of this cut and glue quantum surfaces using SLD curves and implementing this recipe to obtain a few formulas. And the rest of my talk, I will just present 3 results that we obtained using this recipe. So, I will just present like what kind of cutting glue picture we are using and what is the result that we get. So I will not explain any details. So the first is that you can glue together two. So you can glue together a quantum disk with 2 boundary mark points with a quantum disk with a 1 bulk point and 1 boundary point. And the consequence is a quantum disk with a 1 bulk point, 1 boundary point, together with the SLD curve, which is how this topology. So this is a variant of this cut and glue picture using SLD to cut quantum surfaces. And using this picture, what we are able to do is we are able to compute the 1-point function for Liouville CFT in the boundary case. So remember, so when I explained this bulk case, I mentioned a formula called DOZZ formula, which is a bit complicated. And in the boundary case, I only gave a definition. I didn't mention any formula because the analog of the DOZZ formula is only proved here. It's called the FZZ formula, which is conjectured by 3 physicists. So it appears to be the case that the proof of DOZZ formula doesn't work for this FZZ case. And as far as I know, the only way to prove it for now is to use this picture. And along the way, we prove this formula. We also prove something for this mating trees theorem. As I mentioned in the mating trees theorem, if you have the general parameters, the Brownian motion is correlated, and the correlation is given by this. But in the original paper of 2018 in the Sheffield, they left the open question of determining the variance of the Brown motion. And we showed that the variance of Brown motion is this. And the way we do it is actually a very interesting interplay between these two kinds of approach. So the history is that the first, in the case of mu equal to 0, this one-point function was computed by Guillaume Remy a few years ago, and this is equivalent to a famous formula in the matrix called the Theodore-Boutroff formula for derivative Gaussian class. And then based on Guillaume's result, Remy's result, using this cutting green picture, we first get this making trees variance, and then using this making trees term together with this value, we complete the proof of this as the formula, which is the this formula with mu not. So there is an interplay between these two kinds of integrabilities. Okay, so the next result is about SLE itself. And I think this result is also a result that could let people sleep. So maybe I don't spend too much time on this result, which basically there are some interesting variant of SLE called SLE kappa rho. And in this SLE kappa rho, you can compute some natural quantity related to conformal derivative. And we give a formula for this quantity. And this formula, so all these formulas will also appear in this DOD formula. And so these kind of formulas is not easy to get if you just use SLE method, just by the nature of these formulas. And this is what we do. So I will save you some time to read the full details of this theorem. So the last one is a bit more interesting. This is a so-called imaginary DUZ formula. So the imaginary DUZ formula is related to the DUZ formula by taking the inverse, and you also need to relate the parameters. So the DUZ formula has 3 parameters, which is alpha 1, alpha 2, alpha 3. This corresponding to the 3 weights of these 3 points, the locations. And the imaginary DUZ formula is one over DUZ formula, but you need to relate all the parameters using a relation called PPZ relation, which I didn't define. But this is something proposed by Xin, which has some significance in conformal field theory. And there is a conjecture by Vinti saying that if you consider the so-called 3-point function of this CLD kappa is given by this imaginary DZ formula. So let me just give the case kappa equal to 6. So kappa equal to 6, this CLD 6 is the scaling limit of percolation. So the content of this conjecture is just saying that if you have 3 points on the plane and you ask what's the probability that they are lying on the same percolation cluster, this probability will converge to a certain quantity. And so I consider the probability that 3 points, they are in the same percolation cluster. And as this delta tends to 0, this will converge to a certain quantity. And this quantity is lattice dependent. So although this percolation has some universal scaling limit, if you look at this probability, there are some lattice dependent constants. But you can remove this lattice dependence by considering the following. This is maybe P3, this is P2. So what I'm doing here is I'm using this. I'm using the probability that 3 points are on the same percolation cluster divided by the product of 2 points on the same cluster and take a square root. And then as delta tends to 0, this limit will converge to a limit that does not depend on the underlying lattice of percolation. And this number is a universal number, only depends on the scaling limit of percolation, which is called CLE6. And this Daphne-Vinti conjecture says this limit equals to this. In the case gamma equal to square root a3. And the reason you put this parameter here is that there are some relation called PTZ relation, and this relation is a relation about some like a dimension of certain fractals in the Euclidean geometry and the quantum geometry, and this particular number is the output of this formula. So this is a conjecture by Daphne and Venti. This conjecture is very nice because it computes something about population, but so one drawback of this conjecture is that so in the DUGD formula, all of these three numbers can vary, right? But in this conjecture, I can only have this thing. They are being the same. It has to be this particular value. So I mean, I can use this conjecture as a probabilistic representation of this imaginary DUGD formula, but only for some set value. And then later, there's a conjecture by physicists that can give a CLD representation of a general imaginary DUGD formula. So what they conjecture is that if I consider this so-called conformal loop ensemble, which is a scaling limit of these lattice models, and then I can consider a certain quantity of this conformal loop ensemble, which it models how do you count the number of loops surrounding these different points. And this in the continuum limit, it is captured by the joint moment of the so-called conformal radius of these outermost loops. And the conjecture by these people is that this guy is equal to the imaginary DUGD formula. And this is what we proved. So this is our last result that I want to present. So one thing I want to mention is that the regime that we prove this result does not currently cover this conjecture. So technically speaking, this conjecture on population is still open, but I think a modulo some writing, we can also prove this conjecture, but we haven't worked it out. Okay, so here's a summary. So I have explained two ways of sampling natural quantum surfaces, and these two ways are, in some sense, in a very precise sense, equivalent. And there are, and from these two ways of sampling random surfaces, there are two types of integrability that can produce very powerful formulas. And by combining these two integrabilities using the Cartesian Gaussian random surfaces, we can get new results in both directions, and also some new results about SLE and CLE. Thanks.
Really great question. So how close is what you're doing to the way the physicists originally arrived?
It's like, okay, so, yeah, okay, yeah, this is a good. So I think, so the way that the physicists derive this conjecture is basically just based on some generic CFT principle, and then do some simulation. So at least from that point of view, they are not so related. But on the other hand, those CFT principle, so homologically, he already observed that the imaginary DUGD formula times the DUGD formula, they must produce something very simple. So in this case, the imaginary DUGD formula times the DUGD formula is a very simple thing. And this motivates us to think about this coupling between SLE and LQG, because this coupling is also an independent coupling. And on this side, we have random motion, which is simple. And this motivates us to think that we can use this type of coupling to prove this conjecture.
I had another question. So these formulas that come up, like these functions that you get where it's the product will be, I'm not sure like, do these functions come from the solution, some functional?
Yeah. So basically, so this gamma function, it is a solution of this, right? And this, what I showed, so there are some like a triangle here. This is some similar thing, but more evolved. Yeah.
But like the whole expression. is
The
like-
whole version is also a solution of some shape equation. Yeah. And that's actually how they test this one.
So how did it, kind of a general question here, how did the physicists view all the recent progress in the mathematics world on this? Or is it seen as?
I would say, I think, so one thing is that my result is pretty recent, but I think these three physicists, they consider this as pretty good. So they were surprised that we can prove this. But anyway, but these are only these three people. But on the other hand, this result by Rose and Vargas and Kupanin, let me see if I can find these results. Right, so these things are highly regarded. They are even like a conceptually new things.
Okay, well, thanks. Ian.
Thank you.
Try that.
So I mean, this function, so like this whole thing with the ratio of labor.
Your, how do you pronounce your name? Matan, okay. Okay, I guess I can stop the recording for a moment.